little bit too much.
You know, Dr. Palmaz, you have been recognized worldwide, inducted into the National Inventors Hall of Fame. What can we, thus little guys in Reading, do? Except for a few words from the bottom of our heart that reads, for your generous commitment of time, like today, for your outstanding vision, dedication, and excellence, and most important, on behalf of those in need. Thank you for your prayer.
Well, 10 years ago I came and they gave me the city key, and I didn't bring it in my key holder because it was large. But I mean, it's always a pleasure to be here. I mean, how can I not accept, and thank you again for the opportunity, and incredible that you put together that. It's really brought great memories, and some of them good, some of them not so good, but I mean, it is amazing. So I'm going to give a talk. I mean, it's just a few words, really. I mean, it's 14 slides, so very short. But it's a little bit about a subject which, you know, it's not intended to be a negative subject or to cast essentially a shadow over the development of all these devices. It's simply my perception of where my original dream went. And I'm not talking about the device technology itself. In other words, the devices. You know, the devices, the cardiovascular devices, have promoted a new specialty, and the societal benefit is obvious, and the development of the infrastructure, namely places like your institute, have been incredible, and the benefit is palpable, is evident. I mean, I don't know if we have anything to do with that rapid decline in cardiovascular mortality between the mid-2000s until recently. They didn't like that little thing going up at the end, 2014. But at any rate, let me just tell you a few of my ideas, and they're intended only to be a criticism with a constructive attitude. So I assume that this press. Yeah, thank you. Yeah. All right. So this is essentially my own perception of where the trend of progress or regress in cardiovascular technology has been for the past 25 years. Obviously, in my view, the fastest acceleration in progress was during the first years. I mean, from the 80s to the 90s. That's when all the new materials were, you know, they were used, all the new fabrication methods. And I'm talking pretty much like an engineer now, more than a physician. But the medical society really embraced this technology, and they use all their skills to advance it. And without their skills, this would not have been possible. The Palmaz stent was a very difficult device to use, and I was really doubtful that was going to be massively adopted. Simply, it was so difficult. It required very large, you know, great skills to be able to use it in patients, particularly like Mother Teresa with teeny coronary arteries. But you know, Kirsten, who was the one that put it in her, he was very skilled, and so was Richard when he did all the, you know, all the patients that were recruited during those years, and until the trials, you know, were essentially completed and the approval came, which was many years later. Started in '78. The first approval for the Palmaz stent was in 1990. And for the coronary stent in '94. So I mean, obviously there was a lot of work in between. But my perception is that the technological progress of the cardiovascular stent actually went slightly in a different direction, which I was anticipating. I wrote about 6 editorials, 5 or 6 over the years, and most of them about the present and the future. So what was my vision of the future? My vision of the future was great. I thought we were going to be by the turn of the millennium, I thought the stent was going to be very different from what eventually it is today, really. So, but the drug-eluting stent was not my choice of a technological shift. The paradigm of injury and modulation with anti-inflammatory drugs incorporated into the platform was not exactly what I envisioned. I envisioned more like a bio-friendly or biomimetic approach to the device. So I will talk a little bit about that. But definitely the implantable valve, the transluminal valve, was a combination of technologies like a balloon expandable stent or self-expanding stent with a pre-existing biological valve. And to me, that was more of the genius into that was actually the ones that made it possible by using it. So it was the medical community that, again, embraced it and made it possible. So, and then the bio-resorbable stent, I never saw it as a possibility. And lately, the bad news that we heard about the bio-resorbable stent, I expected them. So I think at that point, we're in a decline of technology in the past 10 years, or at least the rate of progress has been severely slowed down. And I think there's a few things that I can see. Of course, the medical community has some responsibility in that they are the ones that drive progress by requesting things. I think the enthusiasm is obvious, and the skills and the talent of the doctors is pretty amazing. But I think what they have been lacking is the demand for new progress, for new things. I think you guys have been very accepting of the status quo. And my perception of how industry, which is responsible largely for how these things are driven, has shifted from 2005 onwards. And to a certain, I don't know if that is because of this Sunshine Act or the cardiovascular device tax, and all those things were negative for the development of these devices, but there's other things too. So, before 2005, the investments in the development of cardiovascular devices was largely corporate, and the goals were long. They knew, for example, when Johnson & Johnson got into this, they were going to be in there for the long run. They knew that there was going to be, not like they were going to have it done in a few years. They were going also for breakthrough projects, where they were going to be the kings of the market, and they were going to destroy the competition. That was the attitude. So a bold, big vision attitude. Of course, they were not afraid to incur into a large financial risk, which they did, okay? And the projects typically were a little bit blue sky. So they went for bold things, change the world kind of thing. Okay, since 2005 to the present, the big corporate sponsors have changed attitudes. Now is the world of the venture capital and the small entrepreneur, many of them ex-employees of these large companies, forming a coalition for small projects, small incremental projects, short-term goals, 1 to 3 years, incremental improvements, because you cannot, with that paradigm, actually create big things. You cannot develop something like a new self-assembled nanoblock or something like that, all right? Small financial risk, it's in the few $1 million, all right? And typically the projects, low-tech, brick and mortar. In other words, incremental improvement. So, I like this review that I wrote for Ted Dietrich. He asked me to do it in the Journal of Vascular Therapy about, I think it's about 10 years ago. So I was, forecasting what was going to happen in the next 10 years, all right? And my mind was full of these dreamy thoughts of MEMS, cantilever, motion accelerators, RFIDs, external controllers, devices like a stent platform transmitted viable data with using essentially biological detectors to the outside, nanoblocks actually completing the structure of a nanoblock to allow for tissue interaction with the materials. The material would be essentially a frame, pretty much connective tissue is. So I thought it was going to be something like that. And I put it all there, and I thought I was pretty happy with all that idea. Well, nothing of that happened. I mean, none of that. Instead, we had the drug-eluting stent, okay? And I saw that as a way to sweep under the rug all the concerns that we had about materials. At that time, I mean, I knew that we had, the minute, besides Mother Teresa, my concern was about the stuff we were using. We were using medical tubing, which was a few dollars a foot, to make devices which were supposed to save a patient's life and live with the patient forever, all right? So, and the materials that we were using actually came from a foundry. They were not very different from the ones that you used to make railroads. So, covering them with a plastic, which on top of that was eluting a powerful anti-inflammatory drug, was to me a bad proposition. This is an insulator. You're using essentially an insulator over a conductive material. The coats are never perfect. They always have defects. So typically you're going to establish electrogalvanic corrosions, niduses of elution of ions into the medium, cells that will live essentially in crevices under anoxic conditions, creation of superoxide radicals, all kinds of bad scenarios, which actually made that proposition actually kind of scary. But nonetheless, and the results were so spectacular. We all know that drug-eluting stent made interventional cardiology king. I mean, restenosis was almost killed, and the thing just took off like a rocket. So the idea of inflammation secondary to injury, using a modulation drug to decrease the degree of response, and it was essentially the model. And the cardiology community adopted it like a prayer. It was it, and everything developed from there. So I would say that over the years, what I saw was a lot of assumptions being used. I found a very cute word for that. It's called heuristic. And if you look it up in the dictionary, it's actually a shortcut in a development program. In other words, an assumption. When you're proposing a new way, a new paradigm, a new idea, and something is missing, then you assume it. And that becomes now the missing block, all right? One of those, essentially, was the promotion of the gold-coated coronary stent. It was assumed that gold was a noble metal. The fabulous in the mouth, for example, was a dental implant. Why not in the coronaries? So, gold cannot do any wrong, isn't it? Well, the Neo-Royale appeared. It was approved by the FDA, and like always, initial results were great, but later on they proved it was not so great. So again, the Neo-Royale disappeared from daily practice, and again left a little bit of a bad taste, particularly people that were oriented towards engineering, because there was never like a essentially go back to it and say, what happened here that went wrong? Why we went into this program, making all these assumptions, and then eventually coming up with a loser device, like was that particular device. Then it came the permanent polymer coronary stent. Of course, today we don't have permanent polymer stents anymore. Now we have biologically friendly, but they have primers, and to a certain extent, we still have the problem of some stuff left behind. All right. So, but it was, as like I mentioned, it was the excuse. So why do we worry about the materials that form the stent? Let's go for mechanical properties. Biological properties are unimportant because now the stent is covered with a coat. So it's just the properties are the coat. Well, wrong assumption. It didn't work like that, as we all know the reasons. And then the bio-resorbable stent. That was, to me, the most amazing heuristic proposition ever. Okay? And there were so many glamorous phrases that I heard over the years. And one of them was my dear friend Antonio Colombo, when he said, he wrote this editorial, said, doing the job and stepping away. And there were others who said the death of the metal stent, and a lot of other assumptions, The idea that you were going to use a device that was going to disappear and leave behind a functional organ was essentially what drove, that was the heuristic principle that drove this program, okay? And the important thing is, the idea was that following reabsorption, which everything will be turned into CO2 and water, all right, the vessel will reorganize all of a sudden out of some miracle into a functional organ. Even we will have vasomotion, which already, you know, this trial failed to prove that. But the more important thing were the compromises we were doing for that reason. We knew that we were using a material that had less radial strength, higher profile, and higher cost. And nonetheless, we still went ahead. And the medical community almost, I couldn't find somebody that would say, this is a failed approach. Everybody loved it. The idea of not leaving anything behind. Maybe it's your guilt, isn't it? Because the cardiac surgeons come and tell you how to deal with your stent, you know, now they have to do a bypass, and now you have something that you're nothing behind. Yeah, it's a guilt issue. All right. So in the world of implantable devices, replacing a diseased organ, in reality, none of those actually pursue the idea of temporary replacement. They all pursue permanent replacement. Nobody would think of a prosthetic hip replacing a degenerated hip joint that a new joint will appear. I mean, no, the metal hip now will be with the patient for life. It's replacing a damaged organ. To a certain extent, a coronary artery with advanced lesions is essentially has lost its backbone. It has no muscular elastic structures. Everything's been replaced by degenerated tissue. So why are we going to think that after we put that thing there, it's going to become now a whole new complex artery with all this incredible complexity that, you know, microscopically a coronary artery has? I think it's a lot of optimistic, naively optimistic thought behind that. So again, ocular lenses, dental implants, all of them are supposed to replace a function for life. So and what we've seen, I don't want to dwell now on this because I wanted to say all these things, but nobody asked my opinion. So, you know, and everybody was marching behind all this. So today now there are evidence that, yeah, even there are ruptured plaques after you place a stent on a vulnerable plaque. I mean, things like that. So essentially it's not doing its job. What the failure in Colombo's prediction was doing the job and stepping away is not doing the job. And then it's stepping away. But anyway, but the other thing is, you know, the large implantable devices. You know, essentially all materials are going into new ideas, brilliant ideas. I mean, I have nothing, I don't take a bit of credit from the ones that have not only thought of this, but, you know, push it forward. It requires a lot of strength and a lot of great big work capacity. But this is old stuff. It's old, and it was old from the, you know, from the beginning. These devices have not evolved. They're still old devices because they're using the same type of metal frame structures. They're using the same, you know, diaphragm, which obviously is essentially a Coke bottle, and the main donor, the contributor to this device is the cow. So, you know, I mean, this is not. I mean, it was okay at the beginning, and it should have led, particularly because of the success it had, should have led to a bigger evolution, at least in my view. So these things are made like little pieces of art, like jewelry, right? Or like a carving a Netske out of a piece of ebony, of ivory. I mean, you see all these hundreds of people doing all this work by work, a little stitch and pass it on, and more stitches and pass it on. There's a million stitches that go into these devices. It's all handmade, and difficult to imagine that something that is medical grade is so labor intensive, you know, and the same thing with the large aortic devices. So, you know, which pretty much to me, they are very similar to the stuff that I was doing at home in my garage. You know, I mean, using wire and pliers. You know, so I would say, you know, just to wrap up, you know, we need to invest more money into all this to push these things into the next generation. It's been great so far, but it's time for a change. We need to change our frame of mind. This thing of injury, you know, followed by modulation with drugs, I mean, has to go by the wayside. We need to abandon that idea. Otherwise, we'll always be stuck with some sort. I mean, it's like nothing works, but then you add the drug, and now you have a viable device. You know, so you know, other industries are pushing enormous amount of investment and effort into things that we don't need until we'll see them. You know, I mean, who needs an iWatch? You know, a stupid thing you need to charge it every night, otherwise it doesn't work. And yet everybody loves it, isn't it? Or who needs a flexible TV screen or an electric supercar? They're totally not needed. But definitely we need to, you know, we need to request that people will be rewarded for developing advanced composite materials. Okay, the way of the future would be something where the stroma, you know, the connective tissue will be prosthetic, and cells will actually integrate with it and give you a functional unit. All right, nanostructured biomaterials that are assembled by itself by using reactive groups, biomimicry platforms and morphing platforms. I wouldn't tell you what it is because otherwise I will give away my ideas, isn't it? I need to patent it first. But at any rate, in my case, you know, it was a time when my job was done. You know, when I finished with the clinical trials, I had to move on and be useful somewhere else. And I became an amateur physical chemist and went into trying to do things. I mean, because of conflict of interest, I cannot tell you what I did, but you know, you need to adapt. I mean, obviously, it was a time where I was not longer needed in the lab, because everybody was doing this better than I was, and it was time for me to contribute somewhere else. But I will always follow the principle that the invention stays with the inventor for life. The most detestable thing in inventions is the serial inventor, a guy that invents something, then forgets about it, whether it's successful or not, and moves on to a completely different invention. That doesn't work. Once you make an invention, you are with it. It's your life. I mean, you stay with for life, hopefully, for life. Okay, you're committed. You need to pursue it, and until you can no longer work, is the time that you stop. And I can assure you, people like Edison and Ford, you know, they would have developed all these things to the very end. Edison would have made the LED, and Ford, at least the Ford Mustang, if they lived long enough, because they were passionate. I mean, those people will not, they were not pursuing economic reward, they were pursuing the ultimate evolution of their idea. So, just to finish a few things, I think the conclusions is, the time for the lone developer working in his garage is gone. You cannot make today a big contribution working with wire and pliers in your garage and a magnifying glass, like I did in the 70s. A significant breakthrough in 2017 is dependent on a large investment, okay, in money and in talent and time, and you have to work in big groups. All right, pretty much like developing a self-assembly nanoblock, it would be as difficult as putting a man on the moon or going to Mars. Okay, and we need to abandon the old paradigms, like this idea of the response to injury, ensuing inflammation, and the use of anti-proliferative drugs as the only way to use implantable devices is a thing of the past. Now we need to go into things biofriendly, biomimicry, and approach devices the same way that we try to develop a new novel drug. You know, understanding receptor and ligand interactions and developing the drug according to that particular need. So, in other words, we need to go forward. That's it. Thank you.
Sit down for a second. I'll have you sit down for a second for a few questions. I love your passion, but this nanotechnology is way above my head.
About mine too.
So if anybody has any questions, but I want to ask you a few questions that I think our audience will enjoy. So is it true, because I've heard, is it true that you actually went to Radio Shack to get some stuff to...
Yeah, that's true. Yeah. I mean, it is absolutely true. And Radio Shack never used it, actually. They went bankrupt now. I mean, they're closing their stores, and they could have used that as advertisement. Because it's absolutely true, yeah. it was a time when you could do those things, you know. Steve Wozniak, and, you know, initially did those things too. They would go to Fry electronic stores and, you know, buy the stuff to put the things at home. You cannot do that today, unfortunately. Now things have become complicated. You need teams where you have to have a physician leading the direction. You need a physical chemist making sure that you stay in the right place. You need nanomolecular engineering. You need a molecular biologist. I mean, all those people working together, well-funded, with the right equipment, then they can make it happen.
Now, it's also my understanding that you thought about this after you went to a lecture, and how did the idea come about?
There's no mystery there. It's just about, you know, being the one that recognizes when somebody poses a problem. You know, Andreas Grunstedt was very, very honest. He was academically honest. The guy, you know, he sounded like he was very happy and dancing around the stage all the time, but he was honest. He said, this is great, but it has a problem, and this is the problem. You see, half the time, the artery doesn't do what you want it to do. And he used things like, examples like putting the foot on fresh snow. He says some plaques are like that. So you balloon expands, but some others don't behave like rubber. You expand it and it comes back. So if you're a little bit mechanically oriented, how can you not think of a frame? It's the obvious thing to use. So I'm not trying to diminish my contribution. My contribution is stating that I stayed with that project for years, and I pursued it, but it was easy to conceptualize.
Questions for Dr. Palmaz?
That would be one avenue. That would be one avenue. Using, for example, you can have nanoparticles with multiple sites, say like a dodecahedron, all right, 12 sites, and each one with a different chemical reactive group. You can actually cause by different means, pharmacologically or physicochemically, reactions to indicate that these things will assemble in a certain sequence. Therefore, you determine shapes. And then by the aggregation of all that, you end up actually building up a microscopic structure from nanoscopic. So that is the idea. Then others is just by simply self-assembly by shapes or electrical charge or by hydrophobicity or hydrophilicity. There's many different other ways to approach that. But it is essentially nanoengineering. There's different ways that you can approach this. Yeah, you could use it. Conceivably, you could use biological or chemical ligands on lesions, so that now will be identifiable by this nano material, and then essentially make a local repair, or you can actually, you know, essentially target a site and determine all this should be actually colonized and so forth. Different ways. I mean, all this is just seeds of ideas that may develop into big projects, but these are big. Remember, the nanoscopic world is the equivalent of the outer space. All right, now we're talking about things that are, you know, 8 to 9 orders of magnitude smaller than what you can see. All right, so you know, getting into that realm is a huge project. It's not a simple thing. But I'm not trying to discourage, but I think that's where the direction should be.
Yes,
Yeah, but
Thank you very much for the talk.
Thank you, Bill.
talk about how it happened in Illinois. You know, can you envision, or do you ever imagine that there will be advances in science that will make stenting and anticoagulant actually obsolete, and that what we're doing with endovascular is kind of like hitting little molecules with a hammer,
Yeah.
and that genetic manipulation might in the future be able to help people steer away from atherosclerotic disease and need for any kind of interventions like this. But that kind of science requires a huge amount of money and universities and people that are willing to do the work. And no one person like you or I can get that off the ground.
Well, that's what I'm saying. Yeah, this project should be undertaken by groups. All right, and you cannot be a lonely guy in his garage. That's for sure. That is over. But you're right. I mean, the nanomolecular engineering. There's a lot already done out there. Don't think that you're delving into a field that is absolutely unknown. There's a lot done. The problem is that many of the groups working in these areas are so misguided because they don't have. There is somebody missing there. Typically, is a doctor, which tells them, this is the application. I mean, this is our need. So stay focused because they go into a rabbit trail like nothing, And next thing you know, they are essentially wasting their resources, And so that's why molecular biologists alone or nanomolecular engineer alone cannot work by themselves and make big decisions in so far direction,
Well, once again, Julio, thank you so very much.
All right, thank you.
Honor and pleasure.
Thank you.
Dr. Palmaz will be around later for any of you who had any questions. I promise you I won't take much of your time. We'll try to finish up. I know it's been a long day. So what I'm going to do, just briefly go on a few of just talk about some of the very salient things on the calendar, just to make sure you understand it. This was our first year that we put this calendar together. And I was hoping this would be a reference, and every year, if any of you have any ideas, please forward your ideas to us. We can make some adjustments. First year is always tough, but this way it's always a reference for you to have. So the most important is on the first slide. There was something that was deleted, I mentioned earlier this morning. These are guidelines on aspirin use for primary prevention. Now, these are the very same guidelines to